Here we go with our question 4. This comes from the electricity and magnetism topic. So I've got the section up there for our from our data booklet. We're told a bunch of information, okay, and we're going to be using these throughout this question. Okay, there's quite a lot going on in this question. We need to come back to these, so don't be surprised if we're flicking around the pages as we go. Okay, let's look at the first question. We're asked about the rods, which have got to have a resistance of no greater than 0.1 ohms. Okay, just the irrelevant bit here being that we know our resistivity, 7.2 times 10 to the minus 7 ohm meters. We're asked to calculate in meters the minimum radius of each rod, and we're going to give our number to an appropriate number of significant figures again. Okay, appropriate probably being 2, given that the resistance itself is to 2 significant figures, as is the resistivity. What else do we know? Okay, we know the length of each rod, which is 12.5 meters. Okay, it's a simple one here. First, just calculate using our equation R equal to rho L over A. Okay, it's written slightly differently in the data book. That's why I just had a little moment of panic. Okay, and we also know the fact that the cross-sectional area, if we're assuming we've got a cylinder, is given by pi r squared, and that's going to help us calculate our radius of each rod. It's a simple insertion of numbers, really. Pi r squared is equal to rho L over r. R is therefore the square root of that expression divided by pi, and we end up with an expression which is 5.35 times 10 to the minus 3, and this is where significant figures comes through. Generally, we quote our answers to the minimum amount of significant figures used. So therefore, if you used a 2 significant figure, then you probably should be reducing that down to a 2 more, and even if it was a 1 significant figure parameter being used, then we should reduce to 1. In this case, it's 2, so we'll stick with 2 significant figures in our answers. But as I've said before, why not just do both? Okay, this is me showing that I've thought about significant figures, but also that I've got the right answer. We're then asked to calculate the maximum number of lamps that can be connected between the rods, and we're asked to neglect the resistance of the rods. Okay, so having done all that stuff with the rods, we're now going to ignore them. Seems a shame. Well, how do we do this? Okay, we recognize the fact that our power supply can do the following. Okay, it can supply a maximum current of 8 amps. Okay, it can supply a maximum current of 8 amps. And we also know a little bit about our lamps. Maybe we'll come back to that in a second. Okay. Let's talk about that now, actually. If we're looking at our lamps, each of them has got a power of 5 watts. Okay. And they can take our potential difference of 24. That's lucky that we're using a 24-volt supply. Okay. Now, because we know the power and we know the voltage, we can therefore, using our equations, I'm just checking they're on the data booklet, they are P equal to VI, there we are. Using P equal to VI, we can calculate the current which is required in each of our lamps. We also know that the maximum current delivered by the cell is 8 amps. Well, if each of those lamps is taking 0.208 amps, because we're working in parallel, therefore we can simply take the ratio of the maximum current deliverable by the current for each lamp, which comes out at 38.4. Now that's not possible to have 0.4 of a lamp. It means that we're going to have to go for 38 lamps. It's always a good idea just to think about that answer in terms of numbers of certain things. We cannot have point something of a lamp, so we'll round it down in this case. We then asked about advantages of lamps being connected in parallel, okay, and one of them being that the other lamps in the circuit remain lit when one of them fails, okay, and there's a few things here. If you look at the mark scheme for this question, I find there's a lot of stuff about kind of just more statements rather than advantages, okay, so I think we would go with something like this. The lamps have the same brightness, okay. They have the same brightness because they have the same potential difference coming across them, and they have the same current going through them, and so therefore they will all have the same brightness. You won't have a system of lamps with different levels of brightness. Okay. Also, another advantage will be that the lamps will be brighter than if they were connected in series. Those are the two ones I would go for here, both connected to brightness. You only need one. Okay. In other words, the lamps don't really affect each other, don't influence each other. They can be independently controlled. All right. Let's go on to the meaty bits. Yes, the step-down transformer. Okay. Step-down transformer is used to transfer energy to the two rods. The primary coil is connected to an alternating main supply, and we're told it's 95% efficient. We're then asked to outline how eddy currents reduce transformer efficiency. Well, let's try and remind ourselves what eddy currents are. Eddy currents come from the fact that from the basic principle of operation of a transformer, which is that we have a changing flux in the primary coil, which then passes through a core into a secondary coil. Now, where the energy is lost is in the core, and that's what we need to discuss about in our answer. Okay, so the magnetic flux in the transformer will change due to a changing magnetic field. In the primary coil, we have an alternating current, which causes an alternating magnetic field, which then induces in our secondary coil. It will also induce an EMF and cause current to flow in the core. Okay, so currents will flow in the core. As a result of current flow, we're going to lose some energy in the form of heat or thermal energy, okay, which therefore reduces the energy transferred to the secondary coil and therefore reduces the transformer efficiency. You're really looking for a story here about the idea that we've got a changing flux in the core. The changing flux induces an EMF and a current in the core, somewhere you need to write in the core, and therefore reducing the energy which is flowing between the two. Okay, this is the nice one here, determining the peak current in the primary coil when operating with a maximum number of lamps. Okay, well, we've got to remember the setup here. We've got our primary coil being connected to the alternating main supply. Okay, so where we've connected our system here, if I just go all the way back out here, okay, our power supply is being connected to the secondary coil. Okay, it's to the secondary coil. So the power out of this power supply is going to depend on what my power supply needs to provide. Okay, well, we know that we've got an EMF of 24 volts and it's supplying a current of 8 amps. So the starting point here is to calculate the power out, sorry about the flicking through here, which is simply 24 times 8, and therefore 192 watts. My power supply needs to deliver that. We know that it is not efficient, okay, which means that the power in, say, the primary coil, okay, has got to be greater than that. And it's greater by a factor of 1 over the efficiency, 0.95. In other words, the power in my primary coil has to be 202 watts, okay, because that's our 190 or 192 divided by 0.95. In the answers, they've rounded it to 190, hence my rounding here as well. Okay, we then think about the fact that the power delivered in an alternating supply can be given by the product of the RMS current and the RMS potential. And so this allows me to calculate a value of the RMS current by using the RMS voltage. We've got 0.84 amps. Well, in the question we're asked what the peak current is, that's I0. You should be aware that I0 is greater than the RMS by a factor of √2, and so therefore we end up with a value of 1.2 amps. It's a really nice question, full of calculations and assumptions and bits of considerations from our electromagnetic induction chapters as well as energy. Okay, so please take the time to look at those 4 steps. There's 1 mark basically for each one, and this is a question I've found that students get very confused by, so do take the time looking at that.